All right, guys. Hello and welcome to another physics video. Today we are talking about relative velocity. All right. So in order to do this, I want you to think about this situation. Okay. Imagine that there are two people. There's one person that is sitting inside of a moving train, and there's another person that is outside of the train sitting on the ground. Okay. My question to you is, who is moving faster? It's a simple question. So go ahead, write down your answer. Who's moving faster? The person in the train that's moving, or the person on the ground? Okay? Well, the answer to this question is it all depends. It depends on who you ask, right? If you ask the person on the ground, well, the person on the ground is seeing the person on the train move by, right? To the person on the ground, the person on the train is faster. They're moving. But think about the person on the train. The person on the train is sitting down, looking out the window. To that person, they don't feel like they're moving at all. But when they look out the window, they see the person on the ground whoosh, fly by. So to the person sitting on the train, they see the person on the ground is actually moving faster. And this is our concept for today. The idea of velocity is relative, okay? If you were floating in the void of space and you were the only thing in existence, would you even know if you were moving? If you couldn't see anything coming towards you or moving away from you, you would have no idea if you were standing still or moving 1,000,000 miles an hour, okay? So this is that concept of relative velocity, right? Also, I apologize if there's an announcement in the middle of this video. Okay. So again, relative velocity is the idea that velocity is always relative with respect to another object. So when you say how fast is something moving, you mean how fast is it moving relative to what? Because if you think about it, right now, you probably are sitting down. So you would say that you're not moving. But if somebody was looking at you from, let's say, the International Space Station, they would see you on Earth spinning around at about 1,000 miles an hour while they were spinning around the Earth, right? So your velocity there is relative. Are you sitting down or are you spinning 1,000 miles an hour? That's a good question. All right. We always have a speed and direction with velocity. So it's always going to have a number, that's the speed, and then a direction, going north, south, east, west, remember, okay? And then last but not least, we have this new word here, okay? What we're talking about is frame of reference. Frame of reference is a super important word. You should write this down, and it means point of view. So what's your point of view? Where are you looking from? Are you sitting on the ground, or are you sitting in the train? Because it makes a difference. Okay, so how do we calculate this? Well, there's two scenarios, okay? The first one is the easy one, okay? But no matter which scenario we have, we're gonna do the same thing. Step number one, you are going to draw a diagram and you're going to have all of the objects in it and all their velocities. So you'll draw like a little box, okay, and you'll draw which direction the velocities are going. Usually this is done for you, okay? The next thing you're going to do is identify whose point of view you're looking through, okay? And then just ask yourself a simple question. From that point of view, does that mean that the other object looks or appears like it's moving faster or slower, okay? If it's faster, you add their velocities together, and if it's slower, you subtract. So let me give you the easy example. The first example assumes that you're on the same ground, all right? So if the two objects are on the same ground, meaning, let's say, in the first example, they weren't on the same ground. One person was on a train, okay, that was moving, and the other person was on the ground. Their grounds are very different. So this is simpler. They're both on the same ground, okay? If they're moving in the same direction, that means that, imagine you're driving on the highway, okay, and you're going 60 miles an hour, and you look at somebody going in the same direction, and they're going 60 miles an hour. Well, to you, that other person is going the exact same speed. So it looks like they're going slower than they really are. They're really moving 60 miles an hour, but to you, it looks like they're going 0. So you subtract their velocities, right? Let's say you're going 60 miles an hour, and let's say the person next to you is going 61 miles an hour, right? Do I have my markers? Here we go. In this case, right, if this person's going 60 and this person's going 61, if red was to look at blue, blue would only look like they were going 1 mile per hour faster because you subtract them because they're going in the same direction. Okay? Whereas down here, if you're going in opposite directions, if you're going towards each other or away from each other, every second that passes, you're getting farther and farther away. Okay? Or you're getting closer and closer together. So in this case, you add the velocities together because they look like they're going faster. So again, to break that down, if you're moving in the opposite direction, okay, every second you're getting farther and farther and farther, or closer and closer and closer. Imagine you're driving head on towards somebody, okay? You both are going faster to each other. You add their velocities. Whereas if you're going in the same direction, it looks like you're going slower. You might as well be in the same car. So you subtract their velocities. Right? Easy stuff, right? He's going 60, he's going 61. 61 minus 60 is 1. Now, what if they're not on the same ground? This is when it gets fun, okay? This is when we get our train problems. So here's your train problem. Here we have a stationary observer off the train, and we have somebody on the train. We love trains when it comes to relative velocity problems. Okay, so we have to look at everything here. We have the train itself is moving 40 miles per hour to the left. We'll call that west. The person on the train, okay, is walking 10 miles per hour east. And then we have somebody on the ground. How fast is the walker relative to the stationary observer? So we got to actually figure out two things here. Okay? Now the first one is this walker. How fast are they moving? Now this is interesting. If you are walking and the ground is moving, this is now a whole new situation. Okay? I call this situation the escalator situation. All right? Or you could also think of it as like a treadmill. If you've ever been on a treadmill at the gym. Okay? The ground underneath you is not staying in one place. It is moving. So you have to ask yourself the question. If the escalator is going down and you're running up the escalator, does that make you go faster or slower? You're trying to run up the up escalator. Well, think about that. It's going to slow you down, right? And similarly, if the escalator is going down and you're running down, or the escalator is going up and you're running up, it's going to make you run even faster, right? Same thing is happening here. The train is going to the west, okay? But the man is running to the east. So it's almost like he's on a treadmill, right? He wants to run this way, but the train's moving this way, okay? Escalator's moving up, or escalator's going down, he's moving up. So if you're moving in the opposite direction of your moving ground, you subtract your velocities. It's going to slow you down, okay? So the train's moving 40 miles per hour, the walker's going 10. That means that the overall walker's velocity is actually 40 minus 10, which is 30 miles per hour. Okay, so as the man on the ground is looking at the walker, he sees the train moving this way, he sees the walker running, which slows him down. So to him, it looked like he's only moving 30 miles an hour because he's not moving. Okay? I know this is tricky. Okay? So remember, email me, ask me questions about this if you don't understand. Let's look at another problem. All right, so here we have another train problem. We have two trains now. Okay? This makes it even trickier. So here, we have the man on the first train. The train is moving east 6 meters per second. Okay, the man is moving east 6 meters per second. The ground and the man are moving in the same direction. So this would be like you turning on the treadmill, and instead of running in the opposite direction of the treadmill, you run, whoa, in the same direction as the treadmill. If you run in the same direction as the treadmill, it's like you get a turbo boost, okay? This you add together. So this would be 1 plus 6, this gives you 7 meters per second going east, right? It would speed them up. Or it's like those platforms at the airport, that moving ground. You know what I'm talking about? Just think about that. Treadmills, moving ground, escalators. Here, this train is moving east, but the man is moving west. So again, we have an opposite here, okay? This is not a turbo boost. This is gonna slow the man down. He's not gonna appear as fast. So we're gonna subtract these, and overall the man is gonna end up going, you always go with the bigger number, 3 meters per second east, okay? So now we have to think about them relative to each other. Well, now that we figured out how fast they're moving on their trains, well, now we have to talk about their shared ground, okay? Both the trains are on the shared ground, and both the trains are moving in the same direction. So to each other, do they look like they're going faster or slower? And as we saw before, they look like they're going slower, right? They're staying right next to each other. So we have to take 7 minus 3, and that gives us 4 meters per second going to east, relative to each other. All right? Let's do one more. Here's a big boy problem, okay? Sorry, not yet. You sit down right there. Okay, so here we have a larger problem, okay? We have a man in a car throwing a ball, okay? The man in the car is driving 20 meters per second, and he throws a ball at 10 meters per second. So the first question is, how fast is this ball moving? Well, imagine this. If you're running forward and you throw something, is that going to speed it up or slow it down? And the answer is that it's going to speed it up. So we have to add 20 and 10. So that ball is moving 30 meters per second east. So let's look at the 3 people. Relative to first man, man A, how fast is the ball moving? Well, the man's standing still. So relative to A, that ball is just moving. And it's moving 30 meters per second east. The second man is running towards the ball. And technically, the ball and the man are on the same ground, if that makes sense, even though the ball is in the air, which means they're coming at each other. And again, if you throw something at something, it's going to speed it up. So we're actually going to add 30 and 5 together to give us 35 meters per second, right? If you're running at something and somebody throws a ball at you, that's going to increase that speed, right? Or if you're running away from each other, that increases the speed. Now the last guy, again, is on a train, which we love. So here's your treadmill problem. The train is moving 10 meters per second east, but the man is running the other direction, all right? So here's the treadmill. Here's the escalator. The escalator's moving up, the man's running down, okay? Or the escalator's moving down and the man's running up. Your question is that going to speed him up or slow him down? The answer is that's going to slow you down, right? It's like he's running on a treadmill. So we're actually going to subtract these two. So this guy is actually moving 5 meters per second, but he's not going this way. He's going this way, right? 10 minus 5 is 5. But the whole train is going to end up moving east, right? Even though he's running this way, the train's faster. So he's not going to be moving west. He's going to be moving east, just slow. So what we do is we're going to take a seat. So what we're going to do here is we see that the ball and the train are moving in the same direction. So it looks like they're moving slower. So this means we're going to subtract 5 from 35, and that gives us 25 meters per second. Again, this is a big dog problem, all right? So the last thing we have to talk about are what if we have right angles, okay? And this is actually easier than you probably think it is, because we've seen these right angles before, okay? A plane is flying 1,000 meters per second south, and the wind is blowing at 25 meters per second west. What's the plane's velocity relative to the ground, okay? So the plane wants to go south, but the wind is blowing west. Well, if you've ever played golf or thrown a frisbee in the wind, you know that even if you want the object to go this direction, if the wind's gonna push it, it's not gonna go straight down, it's gonna go down and to the left. So what happens, So I can do this math before I turn it back on. So what we have here is we have your standard a squared plus b squared equals c squared equation, right? We had our triangle, and again, if you remember that triangle down here, it looked like this. We're looking for c. We knew a and b. A was 100 going down, plus b was 25 going west. That equals c squared. 100 times 100 is 10,000. 25 times 25 is 625. This gives me 10,625 equals c squared. And if I take the square root of both of these bad boys, I get c is equal to the square root of 10,625, which is 103.1. It's right there. Sorry, this is kind of all in the way. But this is exactly what this is saying. See that? The plane wants to go south. The wind pushes it east. It ends up going southwest, excuse me, and it's going at 103, sorry, it's kilometers per hour. We can do one more on these. Okay, same idea, except now we're in a boat. The boat is going 8 meters per second north, but the river is going 3 meters per second east. So what do we see? Well, we have the boat, okay, so we have A, B, we're trying to find C. So we have a squared plus b squared equals c squared. A is 8. B is 6. So we have 8 squared plus 6 squared equals c squared. This is 64 plus 36 equals c squared. This gives us 100 equals c squared, right? 8 times 8 is 64. 6 times 6 is 36. Take the square root of both sides, and you get c is equal to the square root of 100, which is 10 meters per second. All right? Copy down the notes, draw the diagrams, write down the math, and just follow these simple steps, and you'll do great. All right? Email me if you have any questions. Have a great day.